Hello everybody, it is an honor for us to introduce our scientific paper at this international conference in the field of thermal engineering. The name of the article is The Effect of Buoyancy Forces in Building on the Efficiency of Unbalanced Regenerative Air Handling Units. The authors' names are Angel Penev and Lubomir Tsokov, and we are from Bulgaria, Technical University of Sofia Department of Thermal and Refrigeration Engineering. Let's begin with a short introduction. Fixed regenerative heat exchangers are used in the ventilation system for heat recovery of the exhaust air from the room. Compared to industrial generators, which operate under almost constant conditions, regenerators in ventilation system operate under variable climate conditions, variable temperature, humidity, and especially the pressure difference in building. These variable conditions lead to unbalanced regenerator, or in other words, to unbalanced operating mode related to different values of regenerator's efficiency. The difference between external pressure and internal pressure in the building is the stack pressure, the pressure difference, created naturally by the density difference from the air temperature change, or also called buoyancy forces. Unfortunately, these buoyancy forces in multi-story building influence the efficiency of the regenerator and create different airflow into air handling unit and different air change rate on different floor of the building. For this reason, we present a numerical CFD model to study the different airflow in multi-story buildings with natural ventilation coupled with mechanical ventilation in two cases. Case 1 simulates room ventilation with a single operating air handling unit for each room of the building, and Case 2 simulates a pair of units for each room of the building. Next slide is the problem statement, the geometry and dimensions of the buildings. Case 1 and Case 2 are shown on the screen. The building has got 5 identical rooms, connected to the one common chimney vent. As you can see, the regenerative air handling units are integrated into the outward wall of the room. In case 1, air handling units are presented as 5 single domains connected to the main computational domain with 5 inlet vents specified with equal loss coefficients. And in case 2, air handling units are presented as 2 devices operating as a couple in opposite direction for each room. The CFD model are steady state and describe a 3D turbulent flow induced by mechanical and natural ventilation coupled with underflow radiation heating, which create the stack pressure. The models include the mass, momentum with gravity, energy equations coupled with the buoyancy model. The assumptions made for the models are the values of atmospheric parameters are constant and the wind velocity is zero. The air handling unit is modeled as an individual domain with a constant pressure loss coefficient, which describes the resistance of the system, and the use equation is shown on the screen, where delta P is the pressure drop, ρ is the airflow density, and V is the velocity of minimum flow area. And the fans are specified as polynomial function, the relationship between the fan pressure jump and velocity. The numerical simulation will perform at the outlet temperature and pressure. The heat sources are located on the floor of the room with a constant temperature, and the heat flow through the room is modeled by convection and radiation heat transfer. And all of the rest walls are assumed to be adiabatic. The graph on the slide shows a fan curve and 3 resistance curve of the systems, defining 3 points of the fan, A, B, and C. Point B presents the modes of the fan in either temperature condition when the indoor temperature is close to the outside temperature and buoyancy forces are neglected. Point A and C are present when the indoor temperature is higher than the outside temperature, which leads to buoyancy forces in the flow and displays the resistance curve of the system. Point C is the point of the fan when the direction of airflow is through the room, air supply direction. And point A is the point of the fan when the direction of airflow is to the atmosphere, air exhaust direction. This slide shows the results of airflow parameter and the distribution. For case 1, 3 different modes of air handling units were simulated: no working fans, supply airflows, and exhaust airflows. The pressure and velocity distribution present the case when the fans of the device are not working. In this case, only buoyancy forces drove the airflow in the building, and the distribution of the air pressure in the building shows the influence of the stack effect on the velocity distribution. This case 1 presumes only of free open inlets, for example air handling unit without ventilation closed valves. The pressure field for the last two of air handling unit operating mode in case 1 and the pressure field for the simultaneous operating mode as a couple air handling units in case 2 are shown on the screen. The distribution shows the difference between the internal and external pressures for each room of the building, and the fans pressure jump for two operation modes, supply and exhaust airflow. This pressure difference leads to different airflows for two opposite flow directions at the different level in the building. Next slide shows velocity distribution in two cases of air handling unit. Velocity vector field in the room cased by air handling units are shown on the slide. The velocity value of the airflow at each device are averaged for the minimum cross section of the channel. It is important to note that this ventilation scheme allows returning the exhaust air from the chimney into the room and creates unwanted exchange of pollution air between the rooms. In case 2, two air handling units operate simultaneously in a couple for each room, so that as long as one device supplies fresh air and the other device discharges exhaust air. Also this case 2 avoids the disadvantage of bad ventilation of the scheme in case 1 and prevents returning the exhaust air from the chimney into the room. Next slide shows the results of the efficiency of air handling unit. The difference in the magnitude of the hot and cold flow of the regenerator leads to unbalanced operating mode and significantly decrease its temperature ratio and its thermal efficiency. The inlet and outlet air temperature of the regenerators only for case 1 are shown in the graph. The curves for three different floors of the building were calculated using the regenerator mathematical model presented for our previous work. The transient period for which the regenerator reached a quasi-steady state is 8 complete periods. The thermal efficiency during the hot and cold half periods was calculated by equation on the screen, and the overall efficiency of the regenerator was calculated by these equations. As you can see that the value of the efficiency during the heating and cooling period are shown in the table, and they have strongly unbalanced and different values of the floors of the building. And the conclusion of this article are written on the slide. Buoyancy forces in building lead to unbalanced operating modes of decentralized regenerative air handling units. The different rates of hot and cold airflow in the regenerator lead to decrease in the thermal efficiency of air handling unit regenerators depending on the height of the building and the location of the mounting device. When the air handling unit ejects air from the room, the pressure in it decreases and it is possible to return the exhaust air from the ventilation chimney to the room. This can reduce the rate of change of fresh air and create an opportunity for the exchange of pollution air between the floors of the building. The use of pair or synchronized air handling units for one volume ventilation significantly reduces this defect but does not significantly improve the balance of regenerators and their efficiency. We would like to thank you for watching the presentation, and we hope you to understand the essence of our article. Wish you good luck and health and regards from Bulgaria. Take care.